Okay, so here we're looking at 9.3, which is rational functions and their graphs. Okay, so our objective is to find the points of discontinuity and sketch rational function graphs. Okay, so points of discontinuity, that means when the graph is discontinued for a hot second. Okay, so points of discontinuity would be considered, discontinuity, I gotta spell that right. Points of discontinuity would be considered as vertical asymptotes. Some people say asymptotes. It's tomato, tomato. I always say asymptotes. I'll abbreviate that as VA. And then you have holes. Okay, meaning that in a time where in a graph you might have a vertical asymptote where you might have a graph that goes like this and then like that, something kind of like a boomerang almost looking thing, where there's nothing happening where the vertical asymptote is. Another thing is you could have a graph that literally, when I say hole, like there's a hole in the graph, there's no data there. So that's a point of discontinuity. We're going to look at 3 different examples. One big thing is that you have to factor all the time whenever you're finding any points of discontinuity. I'm going to give you them already factored, and so that way that kind of cuts down the time. So to figure out if you have any points of discontinuity, you're always looking at the denominator. And basically you take your binomials that you have factored and you set them equal to 0 and solve. So this is x equals 2, that's x equals 3. Then what you look at is, in the denominator, was I able to reduce this, rational function with the denominator and anything in the numerator? I can't. I don't see anything there. So that means that both of these points, this x equals 2 and x equals 3, those are vertical asymptotes, okay? So if you have, so again, you set any of the binomials equal to 0 and solve. And if they have no other matching binomial in the numerator, that makes it a vertical asymptote, okay? Let's look at another example where I have x minus 2 times x minus 1 all over x minus 2. So again, I look at my denominator for points of discontinuity. I get x equals 2 when I set that equal to 0. Then I look, because now I have to determine, is this a vertical asymptote or is this a hole? So looking at my numerator and denominator, I see that technically I could reduce that down to x minus 1. Because I have a matching binomial in the numerator as I did in the denominator, that makes this a hole. It is very important to distinguish whether or not it's a vertical asymptote or whether it's a hole. Both are points of discontinuity. However, you do need to be a little bit more specific of what kind of point of discontinuity. So now let's look at this third example. I have x minus 3 times x plus 4 all over x minus 3, x minus 3, x plus 4. Okay, so I'm looking at my denominator. All my points of discontinuity, I get x equals 3 and x equals negative 4. Because the 3 happens twice, I don't need to write that again. Now what I want you to look at is, if you notice, the x minus 3's, I only have 1 in the denominator that eliminates. And then my x plus 4's, those totally eliminate. So what I want you to look at is the leftovers. Well, first of all, if you notice the x plus 4's, there's nothing left over. Those are eliminated. They have been reduced. So that means this x equals negative 4, excuse me. Oh, it's not a vertical asymptote. What am I doing? It is a hole because those x plus 4's did eliminate. So that makes it a hole. Okay, however, for this x equals 3, because I have this x minus 3 that was not able to be reduced, that is considered a vertical asymptote. Okay, so when x equals 3, that means I'll have a vertical asymptote. So what I want you to see, just a visual for it, okay, if I have negative 4 and I've got 3. So at x equals 3, I'm going to have a vertical asymptote where I kind of draw that vertical line, just showing that there's a boundary almost. where x equals -4, wherever this graph is at -4, so let's say I've got like a straight line or something like that and it goes through here. What's going to happen is literally I'm going to draw in a hole where x equals -4. That's kind of what it would look like, just to give yourself a little visual for it. Okay, so I want to look at a couple of problems where we need to find the points of discontinuity. And so looking at this problem of x squared minus 4 over x plus 2, again, you need to factor if you can, which I can. That's a difference of squares. So I look here, my point of discontinuity is at x equals -2, and then I need to determine what it is. So because I am able to eliminate that with a binomial in the numerator, that means that what I have here is a hole. Okay, so I have a hole at x equals -2. Let's look at another problem like this. So I have 6x squared plus x minus 2 all over 3x squared plus 17x plus 10. Again, I'm going to need to factor. So you're going to have to do the x method, all that fun stuff. So I'm left with 3x plus 2, 2x minus 1 in the numerator. In the denominator, I get 3x plus 2 and x plus 5. Okay, so my points of discontinuity are x equals -2/3 and x equals -5. So now I need to determine if they're holes or vertical asymptotes. Okay, so the 3x plus 2's, I do have a matching in the numerator where it eliminates. So therefore, the -2/3 is a hole. Okay, and then when x equals -5, if you notice, there's no matching to eliminate, so that would be a vertical asymptote. So that gives you that information there. So those are finding the points of discontinuity. So again, points of discontinuity, you either have a vertical asymptote or you have a hole, okay? Now let's talk about horizontal asymptotes. So horizontal asymptotes, really, you don't necessarily draw them, but what you'll see is that sometimes you almost kind of see an invisible boundary where that horizontal line is. So there are a couple of things. So first of all, if you notice, you can have multiple points of discontinuity. We've seen that already. However, you can have only at most one horizontal asymptote. So while I could have multiple vertical asymptotes, I can only have one at the most horizontal asymptote. The other thing is, to determine a horizontal asymptote, you don't factor. You actually need it in standard form, your numerator and denominator, in order to determine the horizontal asymptote. And so there are 3 different types of horizontal asymptotes and how you discover them. So if the degree in the denominator is bigger than the numerator, your horizontal asymptote is going to be y equals 0 all the time. So if the degree is higher in the denominator than in the numerator, then it's going to be bigger. So for instance, if I have x over x squared, so I'm looking at the degrees. In the numerator, the degree is 1, in the denominator, the degree is 2. The denominator is bigger, so therefore the horizontal asymptote would be y equals 0. The next one, the next type that you could see is if the degree in the numerator is greater than the denominator. Your horizontal asymptote will be y equals none. You really don't even have to write the y equals. You could really just write none if that is the case. So for instance, if I have something like x cubed over x squared, looking here, the 3 is bigger than 2, so the degree is bigger in the numerator, so therefore it's no horizontal asymptote. And then the final one, if the degrees, oh wow, I just spelled digress. That was embarrassing. If the degrees are the same in the numerator and denominator, the horizontal asymptote will be y equals, and it'll actually be the ratio of the coefficients. So for example, if I had 3x squared plus 2 over 4x squared minus 1. My degrees are the same, so then my horizontal asymptote will be y equals 3/4. You just take the coefficients of their of the variable with that same degree. So real quick, looking here, like if I have an example of x plus 2 over 2x squared minus 4. Looking here, the degree is bigger in the denominator, so therefore my horizontal asymptote is y equals 0. Looking at another one, x squared plus 2 over 2x squared minus 1. The degrees are the same, so my horizontal asymptote are the coefficients of that, which would be 1/2. And one final one to look at, if I have x cubed plus x squared plus 3 all over x squared minus 1. If you notice here, the degree is bigger in the numerator, so therefore the horizontal asymptote is none. In the next video, we'll go ahead and look at sketching one of these rational function graphs.